Jai Hind everyone. I am Deepak Narang, Assistant Professor in EN Department of Ajay Kumar Garg Engineering College. The topic of my today's discussion is signal flow graph. Before moving to this topic, we should know the basic idea of why we are using this signal flow graph in this lecture. Basically, in control system, the main thing is to find the transfer function of any system, and the transfer function is that mathematical model of any system which defines the input output relationship of any system, and mathematically it is the ratio of Laplace of output over input, keeping all the initial conditions 0. And to find that transfer function, basically we use two techniques in control system. First is block reduction technique and second is signal flow graph. And block reduction technique is quite complicated than signal flow graph. That is why we generally go for the signal flow graph method. And here we are going to discuss this signal flow graph method. So starting with the contents, first of all, we are going to discuss about its introduction, followed by its terminology, which are associated with SFG, properties of signal flow graph, and construction, how we generally construct a signal flow graph, and how can we convert any given block diagram or given equations to signal flow graph, and lastly, what is that basic Mason-Gain formula through which we can find the overall transfer function of system after converting any system into its signal flow graph form. So first of all, starting with the introduction of this signal flow graph. Signal flow graph is basically a control system which is the simplification form of block diagram, and here the blocks of transfer function, that summing symbols and takeoff points, are eliminated by branches and node. So in this method, the complete block diagram is converted into signal flow graph by eliminating all the summing points. Like if we are having this simple block diagram, we eliminate these such blocks by the term node. Second, it is a graphical representation of variables of a set of linear algebraic equation representing the system is called SFG. So how can we define SFG? It is basically the graphical representation of all the variables which are coming through the linear algebraic equations of a system. A node is assigned to each variable of interest in the system, and branches are used to relate the different variables. And the main advantage of using SFG is that it is a straightforward procedure which is available for finding the transfer function in the complicated signal. That is why we prefer this SFG over the block reduction technique. Now these are basic associated terminologies which are associated in signal flow graph. First of all, node. Now what is a node? A node is that small point or circle in the signal flow graph which basically define the variable of a system. Like here, for example, in this diagram, these small dots are our system variable, and these nodes are represented by a small circle in signal flow graph. Next is, what is input node or source node? This is that node which is having branches only with outgoing signal. For example, this node is having one outgoing signal. This branch is emerging through this node. So this is termed as our source node. Next is output node or sink node. A node which contains branches with entering the signal is known as a output node. Like this node. This is our output node because this branch is entering at this node. So this becomes sink node or output node. And what is mixed node? It is also known as chain node, which consists both the branches which are entering or which are syncing on this node, like our this node, this node. This B node is having both the branches. This is entering and this is outgoing. So this node is acting as both in both ways, that is input as well as output. So it becomes mixed node. Next is branch. A branch is that line in SFG which is generated by joining the two nodes. So this branch basically defines the relationship between the various nodes. For example, if these two nodes are connected in this manner, so these are two branches. These branches are obtained by joining the nodes which are having some relationship among the variables. Next is forward path. A path proceeding from input to output is known as forward path. In the following figure, we can see this path is starting from this and terminating at this output node. So any path which can start from this input node and which is terminating at output node is termed as forward path. For example, here x1, x2, x3, x4, x5, x6, x7 and x8. This is our forward path. Okay. And one thing which should remember in forward path, no node can be repeated more than one time. Okay. If once a node is encountered, it cannot be repeated. If it is getting repeated, then it is no longer a forward path. Second is feedback loop. A loop which is formed through a path starting from a specific node and ending at the same node. Like this, this is our loop. It is starting from this point and terminating at, this is basically self loop. I can take example of this loop. This is starting from this point, and if we follow the path, it is terminating at the same point. So x3, x4, x3, it becomes a loop. Likewise, x5 and x5, it is also a loop. x2, x3, x4, x5, x6 and x2. x2, x3, x4, x5, x6 and x2. Again, it is an example of loop. Next is self loop. A loop which is having only one point, one starting point and the same ending point, like x5, x5. This is our self loop. Now, what is path gain? When the signal flows in the forward path, then product of gain of each branch gives the overall path. If we find the path like forward path x1, x2, x3 and up to x8, so all the gains which are being encountered over any branch, the product of all the gains becomes the path gain of this particular forward path. So its path gain becomes A into B into C into E, G, I and J, if we refer this example. Likewise, loop gain. So like for path gain, the loop gain can be the product of individual gain of branches that is in form of loop is said to be overall loop gain. Like if I take the example of this particular loop, so while traveling along this loop, x3, x4 and x3, whatever gain is encountered, the product of these gains becomes loop gain. So in the same manner, loop gain for x2, x3, x4, x5, x6 and again x2. Its loop gain becomes B, C, E, G and H. This is loop gain for second loop. Next, the main concept is to find out the non-touching loop. Now, what are non-touching loop? These are those loops which do not have any common point in between, so it becomes non-touching loop. For example, like in this x5 loop and x3, x4, x3 loop. These two loops are non-touching loop because they are having no common point between them. But if I say loop x2, x3, x4, x5, x6 and x2 is non-touching, so it is not true because this loop is having common point with this loop as well as this loop. So there is existing only one pair of non-touching loop, that is this loop and this loop. Now, some properties of signal flow graph. So, first property, the signal from a node to another flows through the branch in the direction of arrowhead only. This graphical method is valid only for linear time invariant system. So, this is applicable only for LTI system. It is not applicable for nonlinear or time variant systems. The signal flowing through branch is multiplied by gain, as we discussed one slide before, multiplied gain or transmittance of that branch. This product is equivalent to the node where that branch is terminating. Another crucial property of SFG is that in a particular node, the value of variable will be the algebraic summation of signals coming at that node. For example, if y is equal to, say, this is y and here is x1, here is x2 with gain a, b. So, y becomes a x1 and b x2. That is what this property is indicating, that in a particular node the value of variable will be the algebraic summation of signal coming to that node. This is the algebraic summation of signals. The value of that a node represent is not affected by number of outgoing branches from that particular node. The signal flow graph never unquickly denotes a system. As for a system, multiple graphs can be formed by writing the equations differently. So, there is no uniqueness in the graph because there may be multiple graph for a system which may indicate a system. Next is, how can we construct a signal flow graph? So, for constructing signal flow graph, basically there are two methods. Either we use the linear algebraic equation or secondly we use the block diagram for designing the signal flow graph of a system. So, first of all, if we are having a linear algebraic equation or whatever, so first represent each variable of equation by an individual node. For example, if I am having this equation, so here are three variables y, x1 and x2. So, represent three variables by nodes, say x1, x2 and y. Further, the value of variable at a node is obtained by summing up all the signals coming to that node. We just discussed this point. The coefficient of all variable represent an equation will be the gain of branches, like here these coefficient a and b becomes the gain of branch. Furthermore, locate the input and output variable of the equation in the signal flow graph. So, we'll observe this by following example. Here we can see we are having some variables like y2, y1, y4, y3, y4, and these are coefficients, or we can say gain, and this is system variable. So, first step is to locate all these variables in form of node like this. We have located all the variables y1, y2, y3, y4, y5 and y6 in terms of node. So, what first equation says that y2 is equal to sum of product of a12 into y1 plus a42 y4. It means this is an output node in this equation at which two nodes are coming, y1 and y4, with coefficients a12 and a42. So, this is our this is our input node. So, sorry, this is an input node. So, here which node is coming? y1 is coming to y2 with gain a12, and secondly y4 is also coming to y2 with gain a42. So, we just joining these nodes by using these branches, because this branch is showing the relation of y1, y2 and y3. Next, here now y3 becomes for this particular equation as input, and here we can see y2 and y5 nodes are going to y3 with coefficients a23, a53. So, here y3 becomes input node. Here one branch we will join from y2 to y3 and one from y5 to y3 with coefficients a23 and a53. Next, we can see there is only one node which is coming towards y4 with gain a34. So, we simply join y3 to y4 with this gain. Next, in the same manner, we can say y5 input node which is connected with y4 and y3 with suitable gains. And here we can see y6 is equal to a56. So, we are simply joining this y5 and y6 with gain a56. When we join all these graphs when we merge all these equations into a single graph, it becomes overall signal flow graph of a system. So, this representation is termed as SFG of a system, which we have devised through the linear algebraic equations. Next technique is to convert SFG using the block diagrams. So, in this, represent all the signals, variables, summing point and takeoff point into a node. So, whatever summing point or takeoff point which is a foundation of any block diagram, convert that points into nodes. Second, represent the block as branch in the signal flow graph, and then represent the transfer function inside the given block as gain branch of the SFG. Connect the node as per given block diagram and then represent the gain of the branch. For example, summing point, between summing point and takeoff point. Let us consider this example. Here, all these summing points will be taken as the nodes. This will become node in a SFG. And if we consider the transfer function of this particular block, it will become the branch gain. This will become branch gain. So we can see its equivalent like this. We can see here G1, G2 have become the branch gain of this particular branch, and these have become feedback loops with gain minus H1 and H2. So this is how we can we have replaced all the summing points which were given in the block diagram into various nodes, and the transfer function of having a given block diagram has become the gain of this particular branch. So this is how block is reduced into its SFG. Now after once SFG is done, next is to find the transfer function of overall system. For this, S.J. Mason introduced the idea of signal flow graph for analysis of the system in very easy way. So he proposed a formula which is termed as Mason gain formula, which is the summation of Pi delta I over delta. This Pi is the forward path, number of forward path, and this is the determinant of loops. So numerator part basically deals with the forward path, and the denominator part deals with the looping section. So here we can see, so this part delta, it is found as 1 minus sum of all the individual loop gains. So first of all, we will find the loop gain of each individual loop, and they will be summed in this part, plus sum of gain product of all the possible two non-touching loop. Here we will find the product of those loops which are non-touching with each other, and their product will be summed up here. Next, sum of gain product of all the possible three non-touching loop. If we still find any combination where three non-touching loops are existing, they will be subtracted here, and so on. We'll keep on finding until all the combinations are done. And delta I is obtained from delta by removing the loops which are touching with the forward path. In this, basically, in this term, like Pi delta I, we consider those loops which are non-touching with forward path. Okay. If no forward path is touching with loop, then delta I becomes is equal to 1. So let us consider first example to find the transfer function using this given SFG. So first, as we know, transfer function is equal to summation of Pi delta I upon delta. So first of all, we'll locate how many forward paths are there. So we can see here, we can easily see here there is only one forward path which is starting from input and terminating at output side, and its path gain is G1, G2, G3, G4, G5. Once forward paths are done, next we will find the loops of individual loops of this given SFG. Now locate this. First loop is this. If I trace this loop, so this is our first loop whose gain is minus G1 H1. So this is our first loop minus G1 H1. Second loop is this. its gain is minus G2 H2. Our third loop is this. So G4 and H3. Next loop we can see G4, G5 minus H4. So this is our loop number 4. G4, G5, H3. First of all, we have obtained the forward paths. Next, we have obtained loops. Next is to find the combinations of non-touching loop. So we can see here these two loops cannot be non-touching because they are having one common point. But if I see this particular loop, this is in non-touching with this loop and as well as with this loop. So loop number, this L3 is non-touching with L1. L3 is also non-touching with L2. So we'll make product of these combination. Now see, this loop is also non-touching with this loop, this lower one, G4, G5 minus H4, and this loop is also non-touching with this loop. So we have obtained basically 4 combinations of non-touching loop here. So we have obtained 4 combinations of non-touching loops, this with this as well as this. Okay, this with this as well as with this. Okay. Now can we see any further combination in triplets which are non-touching? No, there is no such combination. So we'll apply the formula. So find out the loop determinant, the denominator part of Mason-Gain formula, which is 1 minus sum of individual loop gains and sum of product of loop gains which are non-touching in pair with each other. Next is to find out delta I, the numerator part. So we are having one forward path P1 which is equal to G1, G2, G3, G4, G5. This forward path is in touch with all the loops. There is as such no combination existing over here where we can see the forward path is non-touching with this loop. So for this, our delta 1 becomes is equal to 1. So we'll apply, put this value into this formula, that is P1 delta 1 over delta, this is our overall transfer function. So G1, G2, G3, G4, G5 into 1 divided by delta which we have obtained in this equation. This is the overall transfer function of this particular example. Next example, which is a bit complicated, we can see here again, first of all find the forward paths. We can see here first forward path is this, that is P1 is equal to G1, G2, G3, G4, and next forward path is, we can see G1, next forward path is this G1, G5, G8 and G4. P2 is equal to G1, G5, G8 and G4. These are two forward paths in this particular diagram. Next is to check the looping section. what are basic loops in this diagram. So first loop is, we can see this is our one loop G1, G2, G9, loop number 1, G1, G2, G9. Other loop is G3, G4, G10. Next loop is L3 is G3, sorry. Next loop is G1, G5, G8, G4, G10 and G9. This is G1, G5, G8, G4, G10, G9. And next loop is L5. We can find this simple G5, G6, and last is L6 is equal to this self loop, which is G7. So we have obtained forward paths and the loop. So next is to find out delta. For delta, we need combination of non-touching loop. Is there any non-touching loop existing in this system? Yes, we can see this G7 loop is non-touching with this loop and this loop. So here we can see there are this combination of non-touching loop existing in this particular problem. G7 is in, we can see G7 non-touching with this loop, G7 also non-touching with this loop. And another loop is, that is G3, G4, G10. Where is G3? This is G3, G4, G10. If I mark with another color, this G3, G4, G10 is also non-touching with this small loop G5, G6. So we have listed out all the combinations of loops and non-touching loops. That so we can simply write delta is equal to 1 minus sum of individual loop gains and the sum of product of loop gains which are non-touching with each other. Now let's just find its delta 1 and delta 2. This forward path is G1, G2, G3 is in non-touch with this. So delta 1 becomes 1 minus sorry, 1 minus G7. Delta 2 is G1, G1, G5, G4 and G1, G5, G8 and G4. This forward path is touching all the loops, so delta 2 becomes as 1. So we will simply apply P1 delta 1 and P2 delta 2 as this is value 1, delta 2 value is 1 and delta 1 is equal to 1 minus G7 into P1 plus P2 into 1 divided by delta, which is obtained by this individual loop and non-touching combinations. So these were few examples which are based upon SFG technique. So if I have a quick revision, what we have discussed in lecture, first of all, definition of SFG, which is basically it's a graphical representation of all the variables which are obtained from the linear algebraic equation, which is basically represent the system, is called SFG. The various terminologies like node, branch, forward path, loop, non-touching loop associated with SFG. How SFG is obtained by using linear algebraic equations and using the block diagram. Then what is Mason gain formula to obtain the transfer function of this system? So this was all about of SFG. Thank you.